So good morning, everyone. First of all, I would like to thank my colleague, Professor Masarakis, who invited me this year too. And as he said, I would like to precise before beginning that I discovered a couple of days earlier that this is a conference enlarged to a very large audience. I mean, engineering audience, physicians, and so on. So I had to, let's say, to consider my initial talk in a different way to make it as understandable as I could. Um, Sorry, I'm engaged. And the purpose of this talk is mainly I cleaned, I would say, all the proofs of the technical aspect it was initially forecasted to deliver in this talk, and I cleaned all of this to keep mainly the ideas which drove this research. This research, I had to precise also that is research I spent several years with my dear colleague, Professor Frank Assus, who is from Ariel University in Samaria in the state of Israel. And so the purpose, as you see, I changed also the title, if you see regarding the menu of today, uh, in the place to rightly speak about a new Taylor-like formula, I prefer to change and to highlight that this research is based on, let's say, a new view regarding the inequalities all of you are used to experiment in a different context. And we will see particularly today the applications of this way of considering these inequalities applied to numerical analysis. So uh, if it is going on. No, yes, it is going on. A couple of minutes to consider the inequalities we are used to consider every day. For example, in calculus. In calculus, you have very, very famous, you will maybe don't consider it like serious, but it is serious as you will see. The triangle inequality is the simple one. And how you use this kind of inequality, you have usually the sum of two numbers, you consider the absolute value, and you would like to upbound. What you are doing naturally, without thinking, without any conscience, anyone, use this inequality. You have maybe another one you can suggest me. But anyway, it is the natural way to consider this inequality. More complex in the framework of functional analysis. Okay, you have this one, which is also very famous. You have the absolute value of a given integral. You would like to upbound. What are you doing? You can do a lot of things, but it is the natural one you consider. You can also use the Cauchy-Schwarz inequality and its generalization. I mean the Holder inequality. On any case, you are considering and you upbound without thinking a little more or less. You have, in particular cases, more complex, more fine, depending on the context, the Hardy inequality. I see that on the left, you don't see, but you can discover what does it mean, Hardy inequality. And I wanted also to recall the famous Poincaré inequality, and we will see why in a few moments, in few minutes. For all of these inequalities, the problem is that no one think about it. You have not any idea regarding the relationship between the two sides. You have not any idea regarding the distance between the two sides. You are bound, but you don't know how much you lost regarding the information when you are bounded with one of these inequality. And this is a crucial problem. For example, if you make a sequence of inequalities and you cannot get the results you would like, you expect. So how do? You come back in the beginning and you try to make the upbounded inequalities finer. But how you can evaluate it is finer or not? To make finer, you have to get an information between the two sides of a given inequalities. And of course, except particular cases, you have not any idea, but it doesn't care. Let's say it doesn't care, but it is very important if you want to improve a process of unbounded inequalities. The last one is more terrible because the last one, even when you can evaluate the two sides, the integral of the square of the function and the integral of the square of the gradient, of any case, you have the constant C of omega, which is completely unknown, depending on omega. Okay, you have famous work like Talenti in Italia and others, but for any domain omega, you have not the numerical value of C of omega. So the distance between the two sides is unknown. This unknownness also appear in a lot of context, for example, in numerical analysis. And this, I heard the speakers before my talk now, you used a lot of finite method, element method, and others numerical approximation. Let's speak now about this. You would like to choose a process, a numerical method to approximate a very complex problem. Let's take the simplest one. It is the first course in numerical analysis, you know, for engineering, for physics, and so on. You would like to evaluate the interpolation error. You have a function f, which is very complex. You don't know it, except several points. Okay, this is the point of interpolation. And for the other point, x, in a given interval AB, you would like to evaluate f of x given the knowledge you have of fx in other points. You measured, for example, in other points, but the analytical expression of fx is completely unknown. So you substitute, you replace f by a polynomial p of x. It is very well known. So you understand, because you substitute, it means that you don't know f of x. If you don't know f of x, the left side of inequality is unknown. So you will not be able at any time to evaluate the distance from something which is unknown to even when the right side, even when it will be known, the right side. But the right side is also unknown. Very nice. Everything is unknown, but it doesn't perturbate anyone. So why the right side is unknown? Because as you see, it appears a constant C1k, which is built, which depends on mainly on the function f, which is unknown as we said at the beginning. And h describes, let's say, to be simple, the mesh size of the interval AB. It is not exactly the mesh size, but you can think about a mesh size. It will be the same problem regarding the unknownness between the two sides regarding interpolation in an approximation of integral. You have an integral, it is impossible to evaluate. You will approximate by SF, which is trapezoidal, Simpson, Gauss, and so on. So the integral is unknown. So the left side is unknown. And then on the right side, you have the same structure with another constant, C2k. So the distance between the two sides is unknown. That is to say, like for the first case, that the accuracy of the approximation, interpolation, or integration approximation is unknown. So how can we choose? How can you choose in a numerical, in an industrial context or in the engineering context? How you choose? Think how you choose a numerical method. We'll see about it later. The same for the approximation of ordinary differential equations. You don't know the solution u. You would like to evaluate at a given point xi. You approximate by a given scheme, Crank-Nicholson, what do you want, Wunsch-Cotta, Taylor. You have a panel of approximations. U till I, it is the approximation. So, of course, naturally, on the left side, it is unknown. And on the right side, or again, it is the same structure. It is very interesting. I will say now, after the next line, why the same structure appears and is very interesting. So, of course, the best and the top, it is the approximation regarding now solution of PDEs, partial differential equations. So here you have a lot of possibilities, finite elements, finite differences, finite volume, and so on, spectral method, and so on. So here you don't measure the error with the absolute value, but with the given norm, which is the distance, more or less, between the exact solution and its approximation util. But on again, I would say, the left side is unknown and the right side, as you see, with the same structure. Before we will see the responsibility of the unknownness of the constant which appear on the right side, let's say that for the left side, we have no solution. It will be unknown, because if it would be known, we had not to make any approximation of f, or u, and so on. So on the left side, it will be unknown forever. Don't believe for any solution on the left side, it is unknown. So understand that the left side is unknown and measures your accuracy of your method, of your approximation method. It's quite a big problem for me to understand that people don't care, implement, use, solution, result, everything is okay, everything is not okay at all, but that's all right, a bit hope. So how people are choosing now, and they have one and only one way to choose and to compare two numerical methods for a given context. For example, let's go for the first one, for interpolation. How you choose the degree of the polynomial. How do you choose? I saw in the previous presentation, the speaker told about second order shape function. Why second order is here? What not the first order? It's not sufficient. It's less expensive. Why not? I worked several years with the CERN in Geneva with the particle accelerators. There, they use 1,000 times the approximation. So the cost is very important. So second order, third order, fourth order is very expensive. So why not to use the first order or the second order? Regarding this estimate, you cannot have a very precise point of view to decide how to choose your numerical method, except, and this is the key for all the world, when h, the mesh size, goes to 0. Of course, if you consider, for example, the first inequality with two polynomials of interpolation k of degree less than or equal to k, or m less than or equal to m, k smaller than smaller than m. So of course, h to the k goes slower to 0 than h to the m. And so people said what? We will choose the interpolation with pm, with a polynomial of degrees m. Why? Because h to the m goes faster to 0 than h to the k. Yes, but it's not realistic for your implementation, for your application. Why? Because in applications, h doesn't go to 0 at all. H is small, but it is fixed. So you cannot apply this point of view, I mean the asymptotic point of view regarding this approximation and this evaluation of the error estimate. The responsibility now regarding the constant on the right side. So we wanted to make them as small as possible, to have an upper bound which is the more precise that it is possible. What is the responsibility of the unknownness of all of these constants? You know it. You know, of course. It is the famous Taylor theorem, which claims that you can transfer information for a given point A to a given point B if you collect sufficiently information at the point A. I mean, the first derivative, the second derivative at the same point. So you can evaluate at the point B the function which is very complex and you don't know it, okay. But as you see, as you know, you cannot evaluate at the point B with precision the function y, because in the Taylor's theorem appears the remainder which depends on the point C, which is between A and B, and you don't know where it is. It is the heritage of the famous Taylor theorem, or you say in English, the mean value theorem also, and itself the generalization of the Rolle's theorem. It exists a point between A and B such that the first derivative is equal to 0. This is the source of all of the problems I recalled now, because the constant C1, C2, C3, and so on depends directly with the remainder. So the purpose of the remainder, which is used to evaluate these constants, as we will see, for any approximation. So the purpose naturally of the research is to minimize the remainder, to transfer the numerical weight of the remainder to the main part of the expansion of the formula of Taylor. This is the purpose of our research since for 2-3 years maximum, because before we did something else I have not the time to explain today. So the purpose was to try to optimize the formula of Taylor, which is responsible of the unknownness I recalled before. How we did it? So I say to you again, no proof, small mathematics, but you will see. People who are interested can see the papers we already published, and we are publishing too at the present. So the classical first order Taylor, you know it. We suppose it is a recall, you know it. You evaluate FA plus H regarding FA and DFA. Okay, you have this nice formula, you have a sufficiently smooth function. Here we defined it on Rn, and we will see application in R3, I mean for physical applications. By the way, let me tell you, because in general, in the engineering environment, you don't think that n can be greater than 4 for physical and engineering applications. For your knowledge, in biology, in marketing and media environment, you have n which is equal to 1,000. So it's not so stupid to make a, let's say, a global framework in Rn. And depending on the application, you will take the right value of n. So here we consider, you understand here, a real function, sufficiently smooth, let's say twice differentiable, and which is defined on an open set U, which will be bounded for this talk, non-empty, it's better, and simply connected. The topological condition is very important for our result, not for this one, you know. Simply connected, I recall you, it is a domain which has no holes, no holes in the domain U. It is important to understand it. And then you see that the remainder, it is very known, is upbounded with this expression. The most important in this recall is that you focus your attention about the thing you know, that the upbound appears with a coefficient which is 1/2, off. This is the standard result. So our purpose, as I said, is to transfer the weight, the numerical weight of the classical remainder epsilon A1H, it is the notation we choose, and to transfer his weight to the main part. But if we decide to transfer to the main part, we have to enrich the main part. How we did it? This is the first results we published last year. We evaluate FA plus H given FA, given DFA. If you want to see a function of one-dimensional function, I mean F prime, but also between A and A plus H, we introduced M minus 1 points, internal points between A and A plus H. It is the reason why we are obliged to consider a domain without holes to be able to define and to evaluate the differential or the first derivative at this point. You also see that we weighted the different differential in the boundaries at A plus H by 1/2m. And for the internal points, we weighted with 1/m only. This weight point with coefficients was found to minimize the numerical weight of the remainder, denoted here epsilon A m plus 1. And then we showed that the new upbound is now like you see. we have 1 over 4m in comparison with, maybe you don't see because this toolbar, you remember 1 over 2. So we minimize, we got an upper bound which is 2m smaller than the classical results, and we will see the consequences in application in a few minutes. I mean, in numerical analysis, in approximations. So in the same way, we generalize, if you allowed me to show you, in the one-dimensional case 1D, we also generalize this theorem to a second order. As you see, it appears lambda 1m, which is exactly equal what we found in the first theorem in the previous chart, exactly 1 over 2m on the boundaries, 1 over m for the internal points between A and B now, because we are in the first dimension. And we did exactly the same for lambda 2m. We introduced also points to compute the weight for the second derivative, such that epsilon 2 am plus 1 will be smaller as possible. And then we found that this how do you say, expression is the correct one to be considered to minimize the remainder. And then we showed that this result is optimum and is minimum for the second order remainder, I would say epsilon 2, second order of the remainder. And then let me recall you that the result for the classical Taylor formula, which is 1 over 6. So in our case, the worst case, it corresponds where we introduce only 1 point, m is equal to 1. Because if we increase m, so 1 over 32m squared will be smaller, okay? So the biggest, the worst in our case is when m is equal to 1. So we have 1 over 32 in comparison with 1 over 6 in Taylor, more than 5 times smaller in our case, only when m is equal to 1. Applications of all of this, as you will see, we conserved the formula I presented to you now, and we took m is equal to 2. That is to say, we have to evaluate f prime at A, f prime at B, and f prime at the middle, A plus B over 2. So we have this formula, and we have the estimation, the upper bound of the remainder. As you see, it is now 1 over 128 in comparison with 6, 1 over 6. So how we can see the consequences now. First, very simple application. You know this function, logarithm Neperian of 1 plus x, and we would like to evaluate f when x is equal to 1. I mean logarithm Neperian of 2. With the classical formula of Taylor, you have this. You can evaluate all the derivatives of f. So you are able to apply the famous second order Taylor formula, and you have this result. You see that it is very rough. Logarithm Neperian of 2 is about 1 over 2 plus a remainder which is smaller than or equal 1 over 3. With the formula I recalled up, we have this estimation. We can compute. You have exactly here the details. And you see that logarithm Neperian of 2 with only the second order is about 0.69 and so on. So it is the famous approximation of logarithm Neperian of 2 we use in all application in physics and engineering and so on. And of course, if it is precise, it means that the remainder will be smaller. But we are not surprised. See, up 1 over 128. Now, with the evaluation of the maximum of m3 small and m capital 3, we can show that you don't see. Yes, you see. You see, we cannot move it. Okay, 1 over, it's less than 1%. I mean, with the new formula, the evaluation is precise with a remainder which is smaller than 1%. Professor Mastorakis, you put heater or cooler?
Some people want to increase air condition,
Ah.
other people
No, I think it is fitter. No, you don't think so? No, no, I joke. It's a joke because I see it's too much. It's too serious for the audience. So I wanted to make a small joke. Ah, he's called. Okay, okay. I will invite him here. It will be hot. Okay, another application. Another application. So this is the simplest one. Now more nearer for the engineering applications and all of the approximation context. Application to finite elements, we will see how we will do it in 2 or 3 charts. It is not simple, but I will try to present it. First of all, this is the formula we consider when m is equal to 2, not more. It is sufficient for our purpose. Of course, I have not recalled, but you understood this, that now the function for the second order is not 2 times derivable, but 3 times derivable. It is called in functional analysis, the function f belongs to C3. You know, this is the space of function which admit continuous derivative until the order 3. C3, it is shorter to say. So if f is C3, if you want to interpolate this function by a polynomial, the classical and standard results in the literature are limited for C3 function only with polynomial which is with degree less than or equal to 2. If you would like to interpolate with a polynomial with a high order, you have to assume that the function is smoother, C4, C6, but maybe it's not the reality, as we will see. I will give you an engineering application afterwards. So let's take the context, which is known in the literature. If you would like to have any idea regarding the error of interpolation with the function which has a third derivatives, which is continuous, C3. So you can only, with standard results, interpolate with this polynomial famous of Lagrange, pi, where you see the well-known expression. Now, if you would like to measure the distance between this polynomial, which is of degree less than or equal to 2, as you see, if you would like to evaluate the distance between this polynomial and the function, you will substitute, you will approximate by this. How do you do? You must change FA, FB, FC, and you will evaluate them by the help of Fx. How you do this? With Taylor. So with this classical Taylor formula in the literature, you can get, for example, this result. The distance, the error, it is important. You make market, how do you say, in economy market analysis, you have not any expression for f of x. You will substitute by this polynomial. How much I lost? How much I will lose? So the error in the classical literature says that if f belongs to C3, you understand what does it mean? The error is upbounded with this coefficient, 1/72 times root of 3. Now, we come back to this part, and we will substitute FA, FB, FC by the formula, which is the new one. What we found? We found this result. We found that the distance, of course, the remainder is smaller. So we have a smaller here consequence in the error of interpolation. You see, nothing to say, only to read 1/100, 1,536 times the same root. But we have to be honest. It is not the distance with the same polynomial. Of course, because in our formula, between FA and Fx, you have FA plus x over 2, the middle point, and the same for B and C. So you see, I denote here pi star, the new polynomial which appear, which is with this expression, the famous polynomial pi of Lagrange, and the perturbation which appears, as I told you, you see, at the point and middle point, for at least. But the most important thing is that the perturbation is like this, is with a degree less than or equal to 3 and not to equal to 2. So it's not honest to compare these two results. If I would like to compare with the classical result of Lagrange, of polynomial of Lagrange, I have to take with the polynomial of Lagrange, which is not pi, but pi 3 with a degree of less than or equal to 3, because our is of degree 3, as you see. And this is the result. This is our result. And with the Lagrange, you have this result. Of any way, of any time, we got, you see, 1,536 times root of 3, it's about 2,700. So the coefficient we got is on any way 2 times smaller than the classical one. It appears with the error of Lagrange polynomial of degree 3, pi 3. But if you are aware about the process I described, of course, the classical results of Lagrange cannot be applied if and only if I suppose that the function is smoother, because it appears the maximum of the and the minimum of the fourth derivative. It means that here this is okay for f with the third derivative C3, but for the literature f here has to be C4. That is to say, as I told you before, for a polynomial of degrees less than or equal to 2, I have a result when f is C3, but I have no result if f is not C4 for a polynomial with degree 3. This is also an upgrade. So these two result of, let's say, approximation of the function, we will see now shortly how they have consequences as you are using to implement with finite element method. What is the relationship? So I had to recall, but I have not the time, all the framework of finite elements to understand really the relationship, but I try to do the best now. The interpolation error. Now let's suppose that f here is the solution of a partial differential equation. So for a family of partial differential equations which are linear of second order and elliptic, like Laplace, like Stokes, like a lot of famous operator you have in physics and engineering applications, you will be able to apply the famous lemma, which is the Sears lemma, which claims on the left side, you have the function f, which is now solution to a partial differential equation, f star h, which is the approximation by finite element. And this error on left is called the error not of interpolation, the error of approximation error. Third lemma claims that it is upbound with the infimum of the distance between f and any fh, which are in an approximation space vh, we choose for our purpose include in polynomial less than or equal to 3. That is to say that there is a constancy. I want it to be as precise as it has to be. So C doesn't care for us, but you can choose, of course, if you choose any FH in the VH, which is included in P3, you have, of course, an upper bound of the infimum, which is the definition of an infimum. So you can choose P star, our polynomial, but you can also choose the famous polynomial P3 of Lagrange. So you understand why the interpolation error has consequence to your approximation error for finite element approximation. Now, to see the consequences between the two possibilities I recalled here. If locally we applied, let's say, a given threshold epsilon. Let's say I would like not to access the interpolation error locally on a mesh for any element of the mesh. I don't want to exceed, to over the value of epsilon, as you see. Because you have these two inequalities with the results I recalled up, Locally, if b minus a you denote is h star with the first estimation, h with the second estimation, you can show by these two inequalities that you gain 2 times less point in a 3D application with our comparison. But again, assume that f, the solution of your engineering problem, is C4. Admit a derivative at the order 4, which is not obligatory at all, as I will show you in a very simple example. But anyway, if I can compare, I know that for my business, for your business, you have to pay 2 times less points for implementation. And if you do it for 1,000 times in time, so you will have a real economy with the new estimation in comparison with the classical one. I have almost finished, but I wanted to show you that, for example, you had in engineering sciences very famous problem. Here you have a beam, which can describe a bridge, for example, and you have external density of forces Fx, uh, which models, for example, people, cars, wind, very complex external actions on the structure. And as a result, you have a displacement for any x between 0 and L, if L is the length of the bridge or the beam. And U of x is solution with simple consideration of solid mechanics to these uh, differential equations. So you will tell me, even when you don't see everything, but you will tell me, so what is the problem? You have here the fourth derivatives of the displacement, which appears. So the solution belongs to C4. The solution belongs to C4. This is the point of view 100 years ago. The new view of a lot of, I'm sure a lot of people here know this point of view, is to consider the fourth derivatives depending on what? F, because it is equal more or less with the sign, with the minus. So if F is not so bad, if F is not so hot as I am, so the fourth derivative is the classical one. And so you don't need the new estimation I presented to you before, because you, if C4, you have the classical estimate for Lagrange, and you are quite. But if F is more realistic for engineering applications, let's say with an energy, finite energy, it's complex. We have discontinuities, but you have, and you know it better than I, finite energy. In terms of mathematical consideration, it is called F belongs to L2. It is the space of function such that the energy of the function is finite. The integral of the square is finite. Okay. So if F belongs to this space, that means that the derivative, the fourth derivative is equal to F, more or less. So also U belongs to, the fourth derivative also belongs to the same space than F. You understand it? It is the reason why that people consider that U belongs to the famous Sobolev space, which claims that U has not the classical derivative, but weak derivative. It means that the fourth derivatives and all the previous derivatives before the fourth one only belongs to L2. So the question is, if we have this natural framework, I have not discussed about the boundary conditions, which claims that the section has not rotation and there are not displacement too. This is not so important for my purpose. But for the purpose, if F has a finite energy, the function U is not C4 a priori, let's say, but it is naturally in H4. So the question is, if any function in this space, functional space, can be sufficiently smooth to apply the classical result, I mean C4, but it is not. It is the work of Sobolev. Sobolev in bending claims that any function of H4 only belongs to C3. So you cannot apply all the results you are used to apply. And this is very dangerous. I remember, usually I have time to say more citations about people and colleagues, and my professor, I would say the famous one in numerical analysis, one of the famous one is Pierre and Jacques Williams. Some people maybe knows, and Pierre Arnaud Raviard. Pierre Arnaud Raviard was my professor, let's say, and he said, you know what? He was at the NASA, the year where Columbia explodes. Columbia was Challenger. It was in 70s, around 70, the 70s. And he told people did not consider at the NASA the functional properties, but not functional features. So we compute, we close the eyes, and everything is okay until the crash. The crash appears. What happened? No, it was something we had not turned. You turn it with robot, with all of the things. You have not turned the mathematics. So here you see it's simple that for a bridge, not for a shuttle, for a very simple problem, you cannot apply what you want, and you have estimation to control and to get the best information for the accuracy as you can. Outlooks, and I will conclude now. So of course we have to generalize this work for any order for the Taylor-like formula or Taylor-like theorem, because when you increase the degree of the polynomial of interpolation, so you will need, of course, the same problem with the classical formula of Taylor, with application for which is very famous for high finite elements. High finite elements, people think that no, we are only use 1 degree, degree is equal to 1, 2, 3. You can find in industrial environment which is polynomial with degree less than or equal to 14 to 16. I saw it in the States. So how you control the accuracy? Why you choose this accuracy again? Okay, for other any high numerical approximation methods, I have to stop because even when with the cooler, it doesn't help. Other numerical methods, I mean, other finite elements are also concerned, you understood. Quadrature error estimate. Last year, with the first order we already published for the improved we got for the trapezoidal, and now we have a publication with the Simpson formula, which is depending on the order of interpolation, as you know. So it is not it's not surprise that we have new result for the Simpson this year. And I wanted to finish, as I discussed yesterday with some of you. You have in the industry context, the famous scheme is Runge-Kutta, as you know, which order people every time told me. I met a lot of people every time in France, in States, everywhere. We used Runge-Kutta of order for RK4. Why? They told me, why not? Ah, okay. So you have too much budget because maybe the second order would be sufficient, or maybe it is not sufficient. No, well, I used to do it. Let me sleep. Quiet. Thanks a lot for your attention. Our dear colleague maybe is a bit hot also. So question maybe. Yes. My pleasure. There is no stupid question. Ye- Yes. What is? Okay, so this theorem is optimal for uniform equidistant points between A and A plus H. As you see, you have the same distance between all the points. So we consider weight. It was in the beginning in my presentation, your question. I had to show how we got this formula. And how we introduced weights. Weight before DFA, weight before DFA plus H, weight before the DFA plus KH over M. And we found the weights such that this is smaller, the smallest one. So you have to see the demonstration. It's a lot of intermediate results I had to present. What I can say more, we thought about also a better result than this one. How? Here we choose equidistant points. But for example, if you choose the Chebyshev points, maybe it will be better. If you choose the roots of Hermite or Laguerre polynomial, maybe it will be better. This we don't know. We showed that for only equidistant points between A and A plus H, this result is optimal. This is the result. Yeah. It is only valid, I agree with you, for equidistant points. So you have to choose in your context, but it is not, we are not the first with equidistant points. For example, the famous approximation in integration, Newton-Cotes approximation for integral is based on equidistant points. It's not the first time. You have a lot of situations, but you're right, and it is completely open. I will give you to ask. I see another question, but let me tell you that we thought that we have not found the way to reach this kind of result. Let's consider the famous, not Hermite, not Laguerre, not Legendre, no, not this polynomial, Chebyshev, which is the optimal, as you know, for interpolation. It is the well-known results of Chebyshev points. So let's say we introduce in the place of these equidistant points the roots of Chebyshev polynomials. What kind of result we have? Please, we will be happy to work with you. That's right. Yes. Two? Yeah. H goes to 0. You mean limit not for h goes to 0? I have not looked about this. Yes, it's a nice question. Yeah. 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 Of course. I have to pay. You mean the Lagrange theorem? Okay. I know. I know. Of course, I have not. But you cannot. Yes, but for the second order. Okay, okay, but for the second order, you cannot speak about the mean value theorem. So the generalized mean value theorem with your name. Yeah. Yes, it is the reason why we only say Taylor-like, because it is based on Taylor, and we cooked in a different way, as you see the classical formula. But okay, I accept, of course, your remark. Yes, we have not. You have also the record of the questions.
It's okay.
It's okay.
Well,
Here, I think.
F10, F10.